Okay, so today's linear transformations video, we won't go over any questions, we'll just derive all the 3D matrices that you have to know. So you have to know these three over here, the rotation matrices in 3D and the reflection matrices in 3D. This is the hardest part. Even I've just literally grasped it now and just managed to wrap my head around it. Because it's 3D stuff, deriving it on 2D space, it's a lot harder, of course, because you can't accurately represent it. So the first one, so we had 2D rotations, so the 2D rotation was cos sine minus sine cos. Now the way we derived that by doing the triangles and using trigonometry, it's the same over here. We just have to take into account that there are 3 planes. So if we draw the 3 planes, we've got 2 over here, and like I said, it's not an accurate representation because we're drawing on 2D, but there is the 3rd plane like that, and all of these are at right angles to each other. So we've got a right angle here, this is where it gets 3D, there's a right angle here and a right angle there. Of course it does not look like that, but that's because we're on 2D trying to represent something 3D, which just is not working. So let's say this is the x-axis, this is the y-axis, and this is the z-axis. So coordinates now are going to have a 3rd dimension, so we'll have x, y, z as the vectors. So on the x-axis, this point will have an x value of 1, and it's on the x-axis, so if it was on 2D it would just be 1, 0, but this is going to be 1, 0, 0 because we're taking into account the z-axis now. On the y-axis we'll have 0, 1, 0, and on the z-axis we'll have 0, 0, 1. And this will be represented as, for the x-axis, 1, 0, 0, 0, 1, 0, 0, 0, 1, and this is the 3D or 3x3 identity matrix. Okay, so we are going to do a rotation about the x-axis. Now, if we do a rotation about something, like in 2D, if we have a rotation about a line, so if we have the line y equals x or something, if we rotate stuff around it, the fixed points are on the line y equals x, so they're all invariant. And if we have this, if we rotate it around it, it will rotate, this will rotate, that will rotate. But because our if you imagine a compass, when you're using a compass, you have the fixed point and then you can rotate stuff around it. Just imagine the fixed point, the sharp point of the compass being on the line y equals x, and you're rotating stuff around it. So everything on that line is invariant. So in the same way, because we're rotating about the x-axis is invariant. So the 1, 0, 0 is just going to stay as 1, 0, 0. It's only the others that will change. So what we can do is we can ignore the x-axis. So imagine being on the x-axis and looking straight down it. What you'd see is just this. You'd see the y and z axes, because you're along that, so you'd see this. Now this point, 0, 1, 0, and this point, 0, 0, 1. Now, we're rotating along the x-axis, so imagine we rotate this point so it goes to over here. We'll draw our transformed vector that has a modulus of 1 still, and we've rotated it by angle theta. Now we can do the same here, so we'll rotate it over here by the same angle theta, and this has still got a modulus of 1. And then now it's just the same as what we did for 2D. So this triangle over here, let's draw it out. So we've got a hypotenuse of 1, and then a right angle triangle like this. That's angle theta, and that's 1. Now, along here, this is the y-axis, so this will be the y-coordinate, and this will be the z. Now, because we've got because we'll be dealing in y and z coordinates, the x coordinate, like we said earlier, that's just invariant. So because we're on the y and z axes, the x coordinate is 0. And we're only dealing in whatever the y coordinate is and whatever the z coordinate is. So now we can use trigonometry, and we can say that the y is equal to the cosine of theta, and the z is equal to the sine of theta. Therefore, the vector for yz, like x, y, z, will be cos theta, sine theta. And now putting this into x, y, z, we will get 0 cos theta, sine theta. Now let's look at this triangle over here. This side over here is along the z-axis, so this will be the z-axis, and this one over here is along the y-axis. But because this is the positive y-axis, that's the negative y-axis, so we'll have negative y. Now, again, using trigonometry, we get that negative y is equal to sine theta, so minus sine theta is equal to y, and z is equal to cos theta. So this is going to be 0 because, like we said, we're on the y and z axis, so x is going to be 0. The y coordinate is going to be minus sine theta, and the z is going to be cos theta. Right now, our 1, 0, 0, 0, 1, 0, 0, 0, 1 has been now transformed to, like we said, the x-axis is invariant, so that stays as 1, 0, 0. The second vector, the j vector, was this one, and that got mapped over here, so that's this triangle. So we've got 0 cos theta, sine theta. And then the z or k vector was this triangle corresponding to, so we get 0 minus sine theta, cos theta. And this is our matrix for a rotation about the x-axis. So you see, this matches this. Now this, what we just did, the triangle bits were the same as we did for 2D, but we're just looking at the perspective from the axis we're rotating about. And it's the exact same for the y and z axis. So we just look at those from like that, like POV, and that stays invariant. So now let me do the y-axis. So from the y-axis, if we're looking down the y-axis, we will just see the z and x. So let's draw out the z and x, so it will look like this at like right angles to each other. So that's the z, and that's the x. But this x, even though it's going in this direction, it's still positive because, again, like I said, it's 3D, so it's harder to grasp. But this is the point 1, 0, 0, so it's still the same thing. Just in 2D, this looks like that. So this is the positive direction for the x-axis. So that is still 1, 0, 0. And this is 0, 0, 1. Now we do the same thing. So the y, this will be our final matrix. The y stays invariant, so it's going to be 0, 1, 0. Now, let's rotate this. So the x rotation, we're going anti-clockwise, so that way. So let's rotate it over here. So thus we transform to over here, and we'll draw that. So this will be angle theta, and this will rotate over here, and that will also be angle theta. So now let's look at this triangle. So that's the right angle, this is theta, and this is 1. Now this direction is the x, so that's going to be x, and this direction is positive z, but we're going down now, so that's going to be minus z. So what we've got is x and minus z. Now again, trigonometry. So sine theta is minus z, so z is minus sine theta. Cos theta is x. Now writing this as a vector, as an x, y, z vector, well, x we just said is cos theta, y we said is invariant, so y is still 0, and the z is minus sine theta. So this is our transformed I vector or x vector. Now this triangle, z-axis, x-axis, so the x-axis is this way, so that's going to be x, and that's going to be z. Now again, just some trigonometry. Cosine of theta is z, sine theta is x. So our x, y, z will be sine theta, 0, cos theta. And that is our transformed z or k vector. So now our rotation matrix I, j, k, or x, y, z, well, we just said our I or x vector is cos 0 minus sine, so cos theta, 0 minus sine theta, and then z or k will be sine theta, 0 cos theta. And this matches here. Now hopefully, because we've done 2 examples now, you can hopefully do it yourself for a rotation about the z-axis, so I won't go through that one, but you can kind of see because the z vector will be invariant, so it stays as 0, 0, 1. We will just be dealing in the xy plane, so that looks like that. This j vector will be going anti-clockwise, so over here, that's theta. So the cosine of theta will be y, and because this is positive x, that will be minus x. So minus x is sine theta, minus sine theta is x, which is over here, and then like we just said, cosine theta is y, and then same over here. So hopefully you can understand that. Now, this is the hard one.